Now, I see a lot of you brought in food and drink. Normally, I would be screaming and jumping up and down now because that's absolutely forbidden. But I'm going to lecture for an hour first before we do the lab. And at that point, you'll have to make sure you have nothing that you ever plan on sticking in your mouth in the classroom, because we're going to be working with radioactive materials. And radioactive materials are far more dangerous if you ingest them than if they're around you. And thus, anything you plan on putting in your mouth, you don't want to be around the radioactive materials.
So, would you just part of water bottles? Would that be?
Water bottles you definitely don't want in the classroom when we get to that part.
Do we have to move on that?
You will when we get to that part, yes.
Okay.
Okay, so we're going to talk about radioactivity today because we haven't talked about it yet, and our experiment is exploring radioactivity. So radioactivity, a brief timeline. In 1857, some dude that we've never heard of, I say we, most of us, Claude Felix Abel, whatever that name is, de Saint-Victor, observed that uranium salts emitted radiation that could darken photographic emulsions. And no one took any notice. And then in 1896, so 39 years later, if I'm doing my math right, Antoine-Henri Becquerel rediscovered what had already been discovered. That is, Becquerel was doing some work with uranium salts, rocks with uranium salts in them, and he was doing photography, and he wrapped his photographic plates up very carefully and put them in a dark drawer on top of his rocks. And then the next day when he came to do experiments, he was getting cloudy pictures. And because he was getting cloudy pictures, he thought, well, maybe I did something wrong. He tested and he found that his film already was cloudy, whereas it had been fine the day before. And so he hypothesized that the rocks must have done something to expose his film, even though the film was covered with foil. And so further studies showed indeed that those uranium salts were exposing his film. And that was the beginning of understanding that we could have rocks that give off energy. Let's leave it at energy right now. So then 2 years later, Marie Curie, I can't remember her maiden name. That's kind of too bad. She started her PhD research and started studying this stuff. And so she's the one who came up with the word for radioactivity. Radioactivity is a word that means radiation activity. So she said these rocks are radioactive. And in 1903, she had a couple cool things happen. Number one is she got her doctorate. Number two is she got a Nobel Prize. The first of two. Marie Curie got 2 Nobel Prizes. One in 1903 that she shared with her husband, Pierre, and her, I believe, research advisor, Henri Becquerel. And then one in 1911 in chemistry for the discovery of 2 elements. The 2 elements that she got it for are polonium, which is named after her home country of Poland, and radium. The Curie family is really special. Marie got 2 Nobel Prizes. Her husband, Pierre, obviously got one there because they shared it. And one of her 2 children won a Nobel Prize. And of course, wouldn't it stink to be the last child, the one that didn't get a Nobel Prize in the family? Like, what's wrong with me? I thought it was our family birthright. Anyway, she ended up dying as a result of her research because you know what she didn't know? She didn't know about the dangers of radiation. In 1899, we already talked about Ernest Rutherford in my lecture yesterday. Rutherford published the discovery of 2 types of radiation, alpha and beta are what he called them. And so we're going to look very briefly at these types of radiation and the things we know about radioactivity. So we have 3 types of radiation that we talk about a lot. There's a lot more types of radiation than just these 3. But we have these 3 that we talk about a lot. And so the 3 are alpha, beta, and gamma. And they have those designations for a very simple reason. It's based on their penetrating power. Alpha radiation has virtually no penetrating power. This piece of paper will perfectly protect me from something that's giving off alpha radiation. Whereas beta radiation is much more penetrating. I would need something like, a piece of lead or something to protect me from beta radiation. Gamma radiation, I need really significant protection to protect me from gamma radiation. So that's where the alpha, beta, and gamma types get their designations. But there's, of course, study to be done on what are these. Just knowing how penetrating they are, how easy it is to stop them, is not really telling you much about the radiation. So don't worry, we're not going to have any clicker questions today. This one here is a pretty simple question. Just say, hey, did you pay attention? Beta is in the middle, hence it's the middle one for penetrating power. There is something that we haven't talked about here, and that is the charge of them. So how is the charge determined? Let's just look at this picture. I'm sure I have another picture coming up, but this one's great. If I have the particles go through a magnetic field, you have learned that there is a force when I have a moving charge in a magnetic field. How do you determine the direction of that force? What? Right-hand rule. We have our equation that says the force on a moving charge is QV cross B. So you take your right hand, put your index finger in the direction of the velocity. In my picture, that's up. Put your middle finger in the direction of the magnetic field. So in our picture, that is to your right. And my thumb points, okay, in that picture, the dots are coming closer to us and farther away from us, apparently. So in that picture, I would have a force into the page if Q is positive. But if Q is negative, it's going to reverse the direction of the force. So looking at that, you see one goes into the page, that's the alpha. So the alpha has a positive charge because it goes the direction of the force for a positive charge. So we get that that's a positive charge. And the beta must have a negative charge because it goes the opposite direction. And the gamma goes straight through. What does that tell you about the gamma? It's what? It goes straight through. It's not deviated. If it's not deviated, there is no force acting on it. If there's no force acting on it, what does that tell you? No charge. So the gamma has a zero charge. So we can now also distinguish the alpha, beta, and gamma by their charge. Alphas are positive, betas are negative, and gammas have zero charge. Which statement is true for beta particles? We have to be really careful here. The beta is negatively charged, but there's a thing we call a beta plus. So we distinguish the beta we usually talk about from a beta plus. A beta plus is positively charged. So, of course, what do you suppose scientists do next after they determine that we have these charge differences? They what? Okay, try to find what the actual charges are. Try to find what the masses are. Do these things by crossing magnetic fields and electric fields. And so what they determined was that, okay, actually I've got them coming up, but an alpha particle is 2 protons and 2 neutrons, or a helium 2 plus, because notice there's no electrons. So helium nucleus is an alpha particle. A beta particle, a beta minus, is an electron. A beta plus is a positron, which we indicate with an E and a plus sign. A positron is exactly the same as an electron, except for it has a positive charge instead of a negative charge. And the final one, the gamma particle, a gamma is a photon. It's a particle of light. Now, before I go any further, I need to make something real clear. Where do these particles come from in radioactivity? You probably know, so that's why I'm asking you rather than telling you. Where do they come from? Maybe you don't know. Okay, radioactivity is dealing with the nucleus of an atom. Not with the electrons going around it, but with the nucleus. So these particles are coming out of the nucleus. So let's take uranium. Uranium has 92 protons, and depending on which isotope you're looking at, either a total of 235 or 238 things in the nucleus. So you take that 235 or 238, subtract the 92, and that tells you how many neutrons. It has a lot of protons and a lot of neutrons in the nucleus and nothing else. The nucleus has only protons and neutrons. And so if I have an alpha decay, I had 2 protons and 2 neutrons from the nucleus that broke apart and left as one unit. Does that seem reasonable? Does it seem like something that can happen? It's something that can happen. It takes a little special situation because, why would they come out? Well, the reason they come out is something that took a lot of work. We'll see a picture later up of Maria Geppert-Meyer. Maria Geppert-Meyer, have I talked to you about Maria Geppert-Meyer? Okay, she was, shall we say, a victim of anti-nepotism rules that we used to have. We still have anti-nepotism rules. I was talking yesterday, I was talking to John Turk, who last weekend was talking to the president of Concordia University, who said that his wife can't work at the university because of their anti-nepotism rules. That is, you can't have a husband and wife working at the same institution because it might mean that you showed preference. And those rules back in the day were pretty much exclusively applied. The man gets a job and the woman doesn't. And so her husband worked for University of Chicago, and Maria Geppert-Meyer then was allowed to work but not draw salary, at least not a full-time salary, because her husband already did. The Seventh-day Adventist Church used to have similar policies. There was a lawsuit when I was a child. Mary Kay, that's all I remember for her name, sued because of getting less pay because her husband also worked for the church. And after that lawsuit, now the church pays equal, or does not cut the pay. My wife doesn't make the same as me because she has a different job title. But take the McNeils, they're both being paid full. Just to make sure we're clear on this. Anyway, she was thinking about the nucleus, and she came up with this idea of the nucleus must have energy shells like electrons have energy shells. We'll come back to talking more about the electron energy shells tomorrow in class. By the way, chapter 30 is the last chapter that will be on our next exam. I won't put 31 on it, just 30. This lecture is chapter 31. Tomorrow I'm going to go back and finish chapter 30. So she said there must be energy levels for the nucleus like we have energy levels for the electrons. So I talked briefly last class about the periodic table, and that we have 2 electrons in an s shell, an s orbital, 6 electrons in a p orbital, 10 electrons in, 10 electrons in a p, it's 6 in a d. That's p. No, I was right the first time. 6 in a p, 10 in a d. I should count, but how hard can it be? And so she said there must be similar types of things in the nucleus where there's a lower energy if you fill the shell. And based on this, she proposed that, for instance, 2 must be a number that fills a shell. So 2 protons would fill a shell, 2 neutrons would fill a shell. 2 protons and 2 neutrons would be extra stable. Really funny historical story. She came up with this theory during the Cold War. And so when this information was translated into Russian, at least from what I read, the person who translated it translated the word shell to mean a grenade, like a shell you fire. And so the Russian scientists were reading her ideas, and they thought she was talking about some kind of structure in the nucleus that made the nucleus blow up. And so they were delayed in their understanding by a couple years because of a mistranslation because of the Cold War. Anyhow, she came up with this theory that says that there is stability in the nucleus, and what's happening with the radioactive decay is that you have an unstable configuration. That is something like, let's say that you've taken a bunch of playing cards and you've built a house of cards. It's kind of stable, it stands up, but if the wind blows wrong or somebody bumps the table, it all falls down. That's what's going on in the nucleus. You have a semi-stable structure, But if something jars it just right, and who knows what it is that jars it just right, it will fall into a more stable configuration and things can come flying out. And so the alpha particle could be something that flies out. It could be a beta particle. What's a beta particle? Well, let's stick with the electron. How many electrons do you have in a typical nucleus? None. No electrons in there. How does an electron come out if there are no electrons? It has to have been made. An electron is created in the nucleus and ejected. How do you create an electron? Well, you create an electron by turning energy into mass. And so there is a process by which you annihilate a couple quarks and create a couple other quarks and an electron antineutrino. And so the electron comes flying out with its paired antineutrino. So it's not just the electron that comes flying out. There's a neutral particle. It's called a neutrino because it's neutral and tiny. Anti because it's an antiparticle, which we'll talk about particles and antiparticles in a later lecture. Excuse me. So that's a beta minus. A beta plus is a positron coming out of the nucleus. Once again, how many positrons do you have in the nucleus? None. So once again, the positron is created in the nucleus through a particle interaction. It wasn't there, it's created and ejected. So we'll see slides that show the process a little more carefully, but not to a depth that you would be able to say, oh yes, I can now teach that. So these bottom two answers, a beta particle, some are positively charged, some are negatively charged, so neither C or D would have been the correct answer because some are positive, some are negative. If I'd said a beta minus, then it would have been negative. If I'd said beta positive, it would have been plus. Medical uses for the materials, these are only things that I have had done to me. I damaged my kidney playing football. And so they injected me with a dye, really big stinking needle. I mean, they took it out and I was just freely bleeding. I've never had such a big needle. They made me drink some nasty stuff. Why? Because they wanted to put radioactive particles into my body so that they could see where blood was leaking from my kidney. And fortunately, the leaking had stopped and I did not have to have it removed. It had been leaking. Also, there's the QV or the VQ scan, not QV, ventilation and perfusion. I don't know how those work together. When I had the pulmonary emboli and my lungs were in trouble, I had to have a VQ scan where they, once again, fill you up with radioactive things, and then they test two different ways to see how air is going through your lungs and how blood is going through your lungs. And really kind of scary when the procedure was, well, none of you have had this, right? But some of you will be physicians and maybe some of you might be thinking about radiology. They put this thing on that really restricts your breathing because they want to make sure that you're breathing deeply. And so you're like, I thought I was going to suffocate. And so we do that, and I'm all antsy because it's been hard to breathe. Finally, I can breathe, and And then the guy says, I'm going to have to talk to the doctor before I let you leave. That scared me. It turns out that a quarter of my lungs are dead. But 3/4 work. I'm still better than Lance Armstrong marginally. So those are things that I've had. In medicine, we use these things so you can look for the radioactive emissions and determine where, in my case, blood or air was. We also want to make sure that people like the radiologists don't get a dangerous dose of radiation because radiation can be bad. Why can radiation be bad? It's not enough to say, well, duh, right? Well, duh doesn't mean you understand why it's bad. It's just, well, I've been told it's bad. I believe it. Radiation can be bad because radiation can break bonds. That's the key, right? It all goes back to chemical bonds. Chemical bonds exist because they have a lower energy state than if they were not bonded. When you have energy absorbed, that energy can be absorbed by the bond and break it. And so if you have enough energy to break a bond, it can be dangerous. So light is electromagnetic radiation. We don't worry about the dangers of light radiation because the energy of a photon of light is too low to break any bonds in our bodies. But ultraviolet radiation can start to break bonds. Gamma radiation is ultraviolet radiation with very high energy per photon. So gamma radiation can easily penetrate your body and break bonds. When it breaks those bonds, then you can have things reform incorrectly. Or if you have too many bonds broken, you have too many cells that die, and you can die from what they call radiation sickness. Radiation sickness, you have cells dying faster than your body can repair them, and you expire. And it takes days for you to finally succumb to that, which is not a good way to go, because your tissue is failing, your skin starts breaking apart. Yeah, bad times. So that's why radiation is bad. Something that my wife has been posting about in the last week, cell phones. Cell phones are emitting radiation. They're emitting microwave radiation. Do we worry about microwave radiation?
No.
Typically, no. But then again, we cook our food with microwave radiation. We cook our food with microwave radiation because even though the microwaves don't have enough energy to be absorbed by a bond and break the bond, they do have enough energy to cause the molecules to move faster, which we translate as they're hotter, higher temperature. That's how we cook with it. Well, to some extent, we can then cook our brains with the cell phone. How much? It's a small amount. One research study that I read, they had people with cell phones attached to their heads, and they did not know whether the cell phone was turned on or turned off. And then they studied the changes, and they found that the blood flow was a little bit more on the people that had the cell phones turned on than the people that had them turned off. So there was clearly a physiological response, not very strong. If you just stand up, that made a bigger difference than having the cell phone there. But it is a physiological response. And some people are worried, my wife had me read last night an article, that the cell phones could be very damaging to us. And this is something that there's a lot of research on. Some research finds no negative effects, and some finds negative effects. So it's still an area of active research that we don't have an exact answer on. It's kind of sad because I don't want to give this up. A couple years ago, I was saying that's why I always leave it in my pocket and use headphones. My cousin said, "Really? You think that your pocket's a better place for it? What's that close to?" A very good question. Radiation danger, we talk about radiation damage as somatic or genetic. Somatic damage is damage to things that are not part of the reproductive system. We don't worry about that as much because if it causes damage, it might kill you, but that's going to be the end of it. Whereas genetic damage, if it causes damage and you go on to have children, it could be passed down to your children. That's a much bigger effect. And so because of that, at least historically, they've had regulations about they're different for men versus women. Not because they're trying to be biased against one, but women below the end of reproductive years, we're not allowed to work in high radiation environments. Because women pretty much are born with all of their eggs, and if those eggs are damaged, any time for the rest of their life they have a kid, there's potential of damage to that kid. Men is about every week or so, they completely regenerate their supply, and thus, as long as they don't have a kid while they're working, they're probably not going to pass on a problem, or less likely to pass on a problem. So they had different rules for men and women because of that. So how do we measure it? The traditional way is by having a little folder. I usually bring my thing out, a little thing that you just wear on your pocket, and in there you have some film, and this thing here has, you can't see, it's just not very good quality. This one here is the best. You have different filters that will block different types of radiation with different effectiveness. And so then every month, your badge gets taken, they develop the film, they look at how much exposure you received, and they tell you, by how much the film was darkened, how much radiation went through your body of different types. And We never believe them. When I worked at a Department of Energy lab, we had to wear these things. And one guy said, I don't think that they're really paying attention to this. So he took us with him when he went to Denver. If you live in Denver, you're receiving a radiation dosage that's higher than what's considered a safe background radiation. Why? You're closer to the sky. You have less atmosphere protecting you. Pilots receive a lot more radiation because they're up there high in the sky as well. And so he had his badge there, brings it back, sends it in, and they say, oh yeah, nothing special. We're like, well, there's no way that's possible. But that's just our skepticism playing. Geiger counters. We're going to use actually scintillation detectors, I believe, not Geiger counters. But Geiger counters or Geiger-Müller counters are the most common thing we talk about for measuring radioactivity. Geiger-Müller counters have a charged wire in the center of a barrel. And you have negative charge on the outside, positive on the inside, I believe is the way it is. If you have a radioactive particle travel through here, it can ionize the gas in that tube. And if it ionizes the gas, you're going to have positive charges attracted to the negative charges attracted to the positive, and suddenly you'll get a current that flows between the positive and the negative parts of that barrel. And when you get that current, the detector says, hey, some radioactive particle just flew through the barrel. So it's an ionizing mechanism that you're measuring with that Geiger-Müller detector. So you see things like this, and of course, in the movies, it's always a Geiger-Müller detector. What you have for your experiments, and I'm actually going to have you start to do something with these in just a moment. These are already plugged in and turned on, so they're warmed up by now. These have a high voltage tube in there that's a scintillation detector. What is scintillation? Well, I know you all go home and tell your parents that I provide scintillating lectures, which means that they're bright, brilliant lectures. Right? I know that's what you're telling me. Yeah. So, okay, let's not be honest. So the scintillation detector has a window on it, and that window, when radioactive particles come into the window, it will excite electrons, they'll fall back down and give off light. And that light is the scintillation, and then that light signal is what is detected. They have light amplifiers, things we call photomultiplier tubes in there, that use high voltage. So this is actually what they have. So you have the scintillating material up here at the top, the thing that's going to create a photon when a radioactive particle goes into it, and then that photon creates a photoelectron, which then is multiplied by these diodes in the photomultiplier tube. Each of these diodes is a material that is set at a very positive voltage compared to what's above it. So that thing that says the photocathode has a very negative voltage. And then that first diode is positive by, let's say, 1,000 volts above it. I'm just making up a number. It's probably more like 100 volts. And so the electron is accelerated toward it. It comes in, if it's 100 volts, it comes in with 100 electron volts more energy than it came out with. It came out with approximately 0. Now it's got 100 electron volts. Well, that 100 electron volt slams into this material and knocks off a whole bunch of electrons, like maybe 10 electrons. And then those 10 electrons are accelerated to the next diode that's another 100 volts more positive, slams in, and each one produces 10 more electrons. Now you have 100 electrons. And it continues on going through multiple stages, each one multiplying by as much as 10 times, so that at the end you have a very strong signal, a lot of electrons, produced by just one original photon. So that's what those are. That means they require high voltage. I've already set the voltages on these, so you don't have to do it. Now, let's get started with what we're going to do before the experiment. We're going to be measuring radioactive counts, the activity. The activity is how many decays you had per second. But there's radioactive material all around you. Each person is radioactive in here. And we have radioactive particles flying through the sky all the time. More if you're in Denver, less here. That's why they root for the Broncos in Denver. Right? Radiation damage. So we have only 6 stations. He's not in Denver, so he's got a different excuse. We have 6 different stations, so you'll need to go to one of the 6 stations. We'll have, one group with 4, and all the others will be groups of 3 by 6 times 3 is 18, we have 19, so one group of 4. And the first thing you need to do is what we call a background count. So everybody get to your stations. Okay, I know that pretty much worked for everyone except for there's nobody in one station. And you need to fill yes, sure, I don't care.
Oh,
Well, it works better because you guys don't have one here, they do. But,
I'm up with the other group.
I don't care. So let's get into our groups. And one group will have Ashley in it. She's not here yet.
So are you gonna let them know? Huh? Or just the
We don't know yet.
Yeah.
We don't have observation.
No.
Or test.
No.
We have a test.
You have your one experiment.
Are you guys both going or?
I have no idea. Okay. I thought about it.
So that's the one we have another trigger. Just so you know.
Okay, so I gather Ashley's going to work with you guys, and that's the group 4 back there. Everybody's good? Okay, so the first thing we need to do is to do a background measurement. Now, these detectors, I don't have a picture of it up there. You don't want to mess with the power or the little dial because I've already turned the dial for you. But you have 2 buttons that you're going to mess with. One says reset and one says count. The reset, if you press the reset button, it'll just reset to 0. So it says 0, I hit reset, it stays 0. The count has 2 positions. It has one that says 1 minute. It's actually not reliable by my experience. I wish it was reliable because it would make our experiment easier. But my experience says sometimes it's 50 seconds, sometimes it's 70 seconds, and we need a consistent time if we're going to have reasonable measurements. So the first thing we're going to do is a 15-minute background count. That's measuring the background radiation in the classroom right now. So what you need to do is get a timer and set the timer for 15 minutes. Set it so it will beep at you when you get to 15 minutes. Because 15 minutes from now, you're probably not going to be looking at it and realizing it's time. So set that to 15 minutes, and then simultaneously move this rocker from stop to continuous, that's the middle position, and start the timer. So each group, go ahead and get it started. Once you have it started, we'll not worry about it until your timer goes off. When your timer goes off, you're going to turn it to stop.
To continuous?
Yes, to continuous. So it's the middle position. It's a rocker, so there's middle, there's top. So you're going to, okay, didn't measure it back up pretty well. Yes, but you have to start the timer at the same time.
So set it to continuous. So that's what I just want to.
Okay, so is everybody started now? Any group not started? Okay, just want to make sure we don't have some group like, oh, it delays us. Because our experiment takes 91 minutes. I'm going to lecture for about an hour. That only leaves us a half hour afterward. Now, it'll only take you 2 minutes at most after you finish the lab to finish your write-up. But we want to make sure you get it done. I say at most, unless you didn't do anything during the downtime of the experiment. Okay, types of decay. Oh, I should mention this. I talked about why radioactive decay occurs. What kind of things would make the nucleus unstable? Well, one easy one to understand is the nucleus has protons and neutrons. Protons are positive. What kind of force do we have between protons and other protons? Repulsive. They're pushing apart. So how in the world do you have a nucleus with 2 protons and 2 neutrons? What holds it together? There's a force that we call the strong nuclear force. There's actually 2 forces involved, strong nuclear and weak nuclear. But these are very short-range forces that affect both protons and neutrons equally. So the strong nuclear force holds the nucleus together. And protons are attracted just the same to other protons as they are to neutrons. Neutrons are attracted just the same to neutrons as they are to protons. So this force holds them together. It's very strong, but it's only short range. So in essence, the strong and weak nuclear forces only are affected by the next nearest neighbor. So if you were to take, as an example, the students in this classroom, if they were nucleons in an atom, let's say boys are positive and girls are negative. So if we look at Corso, Corso would be attracted to all of the girls in the classroom. The ones that are farther away, he would be attracted less amount. The ones that are closer, he'd be attracted more. Right? Wrong. Actually, it is right. But how many girls are there in the nucleus? Yeah, none. Right? There's only one type of charged particle. So we have to change that. The boys are positively charged. The girls are neutrons. They're neutral. So there is no attractive force due to charge. But Corso is still going to be attracted to the people right next to him. So he'd be attracted to Noah and to Amanda and to Arden and to James, and everyone else he feels no attraction to. But the electromagnetic force is a long-range force. He would be repelled by all of the boys. So he'd be pushing away Alex, pushing away all of the gentlemen. If you have a small nucleus, you'll have more attractive force than repulsive force, and generally we have about the same number of protons as neutrons. If you get to a larger nucleus, because the repulsive force is a long range, the repulsive force starts to take a bigger chunk. And so the way to make it so we can still have the nucleus stick together is to put particles in that aren't going to be repelled by Corso, but that are still going to be attracted to the particles around them. And so if you put in more neutrons, you space farther apart the positive charges with something that's like a glue holding it together. So with my analogy, the girls are what's holding the nucleus together. The boys are trying to destroy it, because that's what we do. We destroy things. My research for my master's and PhD was all about destroying things. So that's why when you look at stable nuclei, that dashed line would be the same number of neutrons as protons. And that's approximately what we have up until about an atomic number of 20, up until around calcium. After that, you have a very big deviation with a lot more neutrons than protons, because that's necessary to hold it together. Here's the thing on Maria Geppert-Meyer. And yes, she does have a Nobel Prize. I'm going to skip over the uranium decay sequence and just talk about the alpha, beta, gamma, and then the math of what we're doing. So alpha decay. Alpha decay has an alpha particle, 2 protons, 2 neutrons coming out. So let's consider lead. Or not lead, uranium. There's the dominant species, the primary isotope. We call it isotope if it has the same number of protons but different numbers of neutrons for uranium. If that uranium undergoes an alpha decay, it has an alpha particle that has 2 protons and a total atomic number of 4 because it's 2 protons, 2 neutrons. So what we have to have is a balance. We have to have the total number of protons we start with is equal to the total number of protons we end with, neutrons, same thing. So it's going to have plus something else. How many protons am I going to have if I started with 92 and I give up 2? 90. Look back at the periodic table. What element do I have if I have 90 protons? Which one? Thorium. So by the number of protons, you can say immediately which element it is. It's thorium. Which isotope of thorium? Well, I started with 238 total particles. I lost 4 particles. How many do I have left? I have 234. So it's going to produce a thorium-234 after that alpha decay. Now I'll go back to the preceding graph. So it produces thorium-234 right there. Wait, that's uranium. That's a few steps down. I missed the top of the graph. The thorium is up here. The thorium then undergoes 2 beta decays. What's a beta decay? We'll have to look at it in just a second. To become, again, uranium-234, which decays quickly. The uranium-234 becomes thorium-234, so that's an alpha decay. Another alpha decay to become radium-226. Another alpha decay to become radon-222. Another alpha decay to become polonium-218. Then it may either undergo an alpha decay here or a beta decay there. And eventually, after many decays, it will end up as lead, I think it's 206. I don't remember exactly, and I'm not going to make stuff up. I can't believe I cut off the top and bottom of that. So let's look at beta decays. A beta decay is a different beast. Balancing the beta decay is a little bit more tricky because what left the neutron or the nucleus? Not a proton and not a neutron. So if I have a beta decay, let's suppose that our thorium undergoes a beta decay, a beta minus, so it gives off an electron. How many protons are in an electron? None, right? How many neutrons are in an electron? None. So the standard thing that we would do is say that this electron should have subscript and superscript 0 and 0. But this actual decay is a little more interesting. The beta decay is effectively, not exactly, but effectively, a neutron decays into the beta particle plus the antineutrino plus a proton. Now, in terms of charge, I should put that there. My charge is conserved. The electron had a negative charge. The neutrino is neutral. The proton has a positive charge. But the neutron had 0 protons and 1 total protons plus neutrons. What number am I going to have to put down here for the electron to balance? Zero equals 1 plus what? -1. So this beta particle must have an effective -1 proton. It's not actually -1 proton, but it represents a proton that converted into a neutron, thus lowering the number of protons by 1, while keeping the total number of things in the nucleus 0. So my beta minus is written with a 0 on the top because the number of things in the nucleus stays the same, but a -1 on the bottom because the number of protons actually goes up by 1. So now to balance, I have 90 is equal to -1 plus 90 equals -1 plus what number? This is not hard math. 91 plus a -1 gives me 90. So it's got to be 91. And honestly, I don't even know the name of that one. And then taking the top numbers, 234 is equal to 0 plus, pretty clearly 234. So that's the beta decay. Does somebody know what PA stands for? Nope. You do? What is it? That's palladium?
No, it's
Yeah.
Protectinium.
Protactinium. There we go. It's not one that we talk about much. It's naturally occurring because, well, it occurs in this decay sequence. So that's how beta decay works. A little more complicated. Well, what about the beta plus decay then? The beta plus decay is going to be, and I can't think of something that gives off a beta plus decay, so I'm just going to draw the shorthand of it. A proton decays into positron plus an electron neutrino plus a neutron. What's the subscript going to be for this positron? 1 is equal to 0 plus 1. And so that's how you balance the beta plus decays. The positron is a subscript 1 because it's effectively converting a neutron into a proton. Then the gamma decay. The gamma decay I don't have a picture of because the gamma decay works like this. You start with an element and you end with exactly the same element plus a gamma. How does that work? Well, that works like this. Here's my element at an elevated energy state. There's my element after it's decayed. That stopper is exactly the same. But it gave off a sound that you heard. That's what the gamma radiation is. That's an electromagnetic wave taking away the energy difference between the starting state and the ending state. So the gamma does not change anything that we measure about an atom. It's simply changing the energy state of the nucleus. This is, I think, my next to last slide. I put radiometric decay instead of radioactive decay because I started with one slide, changed it to another slide. I did not notice that it did say radioactive. It's supposed to be radioactive decay. From careful study, we know that for each type of radioactive element, there's a certain probability per second that it will decay. Some of them, there's a higher probability per second of decaying than others. But for each element, there's a certain probability of decay. So that means if we measure the activity, which is the rate of decays, the rate of decays will be equal to a constant multiplied by the number of radioactive nuclei we have. So hence my first equation, A for activity. I think our lab uses R for the rate. A for activity is the same thing. The activity, the minus sign is there because the number of nuclei remaining is going to drop. Actually, there shouldn't be a minus sign here. There should be a minus sign there. Wait, did I have that right? Yeah. Yes.
Are these numbers supposed to even out at some point?
No. Supposed to just keep counting.
So you just want to take a measurement?
After 15 minutes, you're going to stop and write down what that number is.
Yeah.
So when it gets to 15 minutes, you're going to flip it to stop and then write down that number. So I'll actually stop because people need to think here. I'll think about where I got my signs wrong here. So everybody now has it stopped?
Is there a number it's supposed to be around?
Nope.
Okay.
It depends on your detector. So everybody has it flipped to stop and I can go on, right? Your time is done, right? Okay, make sure you write down that number and leave it stopped because you won't be starting again until I bring in the radioactive samples and we have to take all the food and gum and whatever out of the classroom before we do that. Question? It's because you have different detectors. They're different at detecting efficiencies. Or it could be that drink's radioactive. If it's got banana, it's more radioactive, right?
No, ours is like 21. Theirs is like 200.
200.
Ours is 295.
288.
Well,
Ours is super radioactive. We'll survive.
yeah. It's just the efficiency of the detectors varies. I may not have put theirs at a high enough voltage, but I put them all on the mark. So I changed one sign, so now my signs are correct. So the activity is going to be this decay constant lambda times the number of nuclei. But the activity is the rate of change. Now, we don't have calculus except for two people here. But with calculus, we would write this equation as dn dt is equal to minus lambda n. I just moved this minus sign across there. And so then you separate variables and integrate. Alex and Corso should be totally down with this. Separate variables and integrate. dn over n is equal to minus lambda dt. Integrate both sides independently, and you get natural log of n over n0 equals minus lambda t. Now, those of you who don't have calculus can just start with that equation. We have that equation we want to solve for n. So how do you get rid of a natural log? Take the, oh, you said e. You use exponential because exponential is the inverse function. So exponential of each side gives you n over n naught equals e to the minus lambda t. So n is equal to n0 e to the minus lambda t. That's going to tell us how many radioactive nuclei we should have at any moment in time. Now, this is based on statistics. You have to have lots and lots of nuclei for this to be an exact number. You have a sample, or you will have a sample, with lots and lots of nuclei. But it's not going to fit this exactly because still it's statistical. It's not an exact equation. So we're going to do an experiment with lots of data points so we can see if this is correct. Now, a couple other things with this. Because n is equal to n0 e to the minus lambda t, but activity is just a constant times n. If I multiply both sides of this equation by lambda, then that gives me that equation. So what we're actually going to be measuring is the activity. We're going to be measuring how many decays per minute are occurring. And we're going to check out the graph. A few more things I have to say. Half-life. Has anybody ever played the game Half-Life? Nope, too old for you?
I loaded it once.
You loaded it once. What's the icon for the game? Lambda. Why is it lambda? We'll see right here. The half-life is the time when n is equal to 1/2 n0. That's the time when half of your radioactive atoms have decayed. Because the number of decays per second is proportional to how many you have, the rate of decay is going to drop over time. And so it's going to take an infinite amount of time for them to all decay. So we measure the half-life, the time when half of them have decayed. And so we can just take our equation, 1/2 n0, that's our n, is equal to n0 e to the minus lambda t, 1/2. And solve this for the half-life, the time that it takes for half of them to survive. It's actually easier if I go back to here before I did the exponential. Because if I take this and take away my blue, that's going to give me natural log of 1/2 n0 over n0 equals minus lambda t 1/2. Whoops, 1/2's going the wrong place. So that means that, notice the n0 over n0, those cancel. So I have minus natural log of 1/2 divided by lambda is equal to the half-life. Nobody likes that minus sign. We also don't like 1/2. Natural log of 1/2 is equal to minus natural log of 2. Just a rule for logs. So this is exactly the same as minus natural log of 2. And of course, then we just write that as natural log of 2 over lambda. So in lab, you are going to find lambda. You're going to analyze your data and find lambda. And then once you've found lambda, you're going to find the half-life and compare that half-life to the accepted value for indium-116, what we're using. I think it's 116. Might be 115. Okay, let's just take a break for a few minutes while everybody gets rid of anything they ever intend on putting in their mouth. So chewing gum, water, juice, energy bars, anything like that. Make sure it's outside of the classroom.